Okay, let's take a quick review of what we have learned today. And last time we discussed about Newton's second law. From that, we get the equation of motion with structure damping here, and also with displacement structure, with the external force. We discussed about linear and average acceleration method. Then we get the Newmark's beta method, which was beta here. And we also introduced a step-by-step simulation to get the seismic response under the ground motion AG. Today, we're going to pick up some knowledge that we left behind for about what is omega and what is damping. This kind of a very basic concept. Maybe you have already learned about free vibration in other lectures, but today let's have a uh, uh, very basic discussion and do a very uh, step-by-step derivation about these equations. So this may help us to understand better about vibration and the ground motion structures themselves. So let's take a look about what is free vibration. Free vibration means that there's no external force, no ground motion. So generally we take just a very simple model like this with a fixed base and with a spring K here and with a mass here, single degree of freedom. And with x, in this direction, only this direction vibration happens. So at a generation at 0 time, we give an initial displacement A and let it go, take it free. After that, what's going to happen is what free vibrations discussion. And no damping free vibration case, we have no external force and no damping force. About acceleration A, they are the second derivation differential of this displacement x. So it would look like this. And for this kind of case, we can have assumption. What kind of solution for the equation? It would be maybe something like this. For example, x equals to a sine omega t. Why? Because if we do one differential of that, we can get omega a cosine omega t, and 2 times of differential, we can get minus omega squared, because cosine to sine, we get minus a omega t. So this part still again is sine omega t, so we get a minus omega squared x. Same thing happens to if we assume that suppose that a equals cosine wave, it will be the same thing. And what is angular frequency omega should we talk about here is sine wave themselves. We have amplitude and we have a horizontal, which is horizontal is angle. So when they come 2 pi, and it will be have come back to where it began. It have period of 2 pi, every 2 pi they have the same wave repeatedly. However, in the vibration issue, we are using the unit of t. So we change theta to time of t. The changing rate is omega. So theta is equals to omega t, and omega will be theta divided by t. So in the looking at the time actual here, and we get the period of t, where t is time period of wave, and repeat it again and again in the unit of seconds. Omega. So when they have when the theta becomes 2 pi, the time t becomes time period of t. So we can get this kind of omega equals 2 pi and t ratio. So this ratio is 2 pi divided by t. And once t is defined, so the omega will be found out. Also, because of the frequency is f, which is inverse of t, so we get omega equals to 2 pi f. Let's go back to the equation of motion of m. We can look at the x2 times differential will be minus omega squared a sine omega t, where x is sine omega t, so it will be minus omega squared x. So put x2 squares this part into here, and we get this equation like this. We can realize that x can be deleted directly because the right side of the equation is 0. So we can get equation like this. So put omega square and m to the other side of the equation, we can get k equals to omega square m. And easily you can get put m back to here, you can get k divided m equals squares omega square. So easily we can get omega will equals to square root k divided by m. So which this equation means is very important. It just means that if the k stiffness structure increase, the frequency of the system will increase, becomes high frequency. So when the stiffness of structure decrease, become a softer structure, then the frequency will become low frequency, which the time period will be longer. So structure isolation is basically use a smaller k so that t will become longer and the response structure will be lower. We will discuss this about later. Same effect can be found in m. So if m is very heavy, the m is larger and the omega becomes smaller, with the time period become longer. Same time, when we lighter the structure, the frequency will increase. So that's why, because omega is equal to square root k divided by m. Let's take the solution for no damping of free vibration. X can be both sine or cosine. So more general probable resolution for X should be a combination of sine and cosine. Thus, we consider A and B is looking like this, so there will be value C that can be defined equal to square root of AB. So it becomes the length of the A and B square root. And its angle should be can be defined by phi. So the sine phi will be AC and cosine phi will be CB, BC. Put into the equation of the solution here, we put the C out and left C under A and B look like this. So because we know that this is sine phi and this is cosine phi, so we put the equation back here. Then we get the result of cosine omega t minus phi here. Realize that phi and c is depending on the initial condition of the equation of motion. So in the 0 point, what is x? What is x dot? What's x2 dot? This means what is x initial displacement, velocity, and acceleration? Will define what is c and phi. However, whenever initial condition it is, the omega frequency is decided by structures a natural nature of k and m. So finally, we get a solution of x equal to c cosine omega t minus phi, or we can say plus or minus is depending on the initial frequency. Or we know because cosine sine is only have the sigma of phi of pi, so then can be also be true if we use c with a sine wave. It's only depending on the phi. So, but omega will be angular frequency will not change, so phi will be the phase angle depending on the initial condition. Maybe some of you have seen the solution that's solved by the exponential function looking like this. So we can also do this in the exponential function. In that way, we can see that x maybe becomes e a t, and velocity and acceleration. Same thing happened is square what becomes x, multiple x, what becomes s2 dot. So to solve that, a square will be asked about plus minus of square root minus km, because this part will be moving to this side, and we get plus minus I with the imaginary number with square root minus 1 and omega, because this part is omega. Okay, so x will be both positive I omega t e exponential and also be AE minus omega t. So the probable resolution will be the combination of these two general resolution. Remember the Euler's formula, E I theta will become cosine theta I sine theta. So omega t here is theta, so we can get using the Euler's formula back here, change them to the this expression back. And getting these two terms together, a plus b omega t, realize that minus omega t will become same with positive omega t. And also with I, a minus b, I. Okay, with minus because of here, minus here, comes out. So this is also same with this part and with another this part. This time, instead of a and b, we use ai minus bi and a plus b as two sides of the triangle, and the c will define it by the square root of this part and this part. Finally, we can get easily of c plus a plus b squared minus a minus b squared, because I squared becomes minus 1. So by solving this equation, we realize this part and this part can be diminuted easily. So it will be 4 times of AB, so it comes out the square root, it will be 2 square root AB for C. Because of easily it comes out of C, so cosine phi and sine phi can be defined like this. As a final solution, we can get back out here. You can see cosine phi, cosine omega t, sine phi, sine omega t, with the C outside. So the final resolution will be x equals C cosine omega t minus phi. Will be the same result as we discussed before. Where C is amplitude and omega angular frequency and phi is the phase angle. So these two kind of method can be finally get the same equation. Next, let's discuss about damped vibration. Here we do not ignore the damping part, CV here, which is C x dot. We also again assume that x equals to EAT here, but by instead of this part into the equation, we can get a squared. This part will become like this, and this part becomes like this, and this is x. So this part by plus part will be the same, so it becomes m a squared c a and k. Thus, due to the equation solving for a, we can get a equals to this equation. I realize that this part, if that is equals 0, then we will have only one resolution. If this part larger than 1, larger than 0, we can have solid 2 resolution. If this part is smaller than 0, so that will be have imaginary resolution. Okay, so this part is very critical. We define when C this part equals 0, this kind of damping ratio here, damping factor here will be the critical damping case. So in the critical damping, C squared minus 4 mk equals 0. Thus, the critical damping C will becomes 2 mk by putting the 4 mk in this side of the equation. And when it becomes 0, this part becomes 0, so C becomes a critical damping C, and A will be defined out like this. It will have a unified result, so only one result here. We can find x equals to E CR 2m T. So in this kind of case, you can see it like the red line in the figure. X will be decreased from the initial value downside to 0 slowly, and with increasing of the t, because the minus here. But in the most case, for the structure, there will be not so much strong damping there. So the damping, real damping, should be some ratio of the critical damping. Here we define the damping ratio H as the real damping factor divided by the critical damping. So C will becomes H time of critical damping, which be 2H square root mk. realize that omega is equals to square km. So we can maybe write the equation more meaningful by multiple m and divided by m. So we can get this part as omega, and the m squared comes out, so 2hm with omega. So if say divided by or normalized by m, we can get that is equal to 2h omega. Means that h time or 2 times of omega will becomes the ratio to mass ratio. Okay, let's take a more detailed look at this part under the square root. So we know that it will becomes 2h omega, so 4h squared and mk minus 4mk. And it will be a 4mk h squared minus 1. So generally, we can a critical damping square and h2 minus 1. Thus, inside the square root, we can get this kind of equation. Put out the CR outside and get h2 minus 1 inside. By change the direction, because we know that in the most case h is smaller than 1, so we put them back looking like this, but with I. Generally, the result will with imaginary number. So only if the resolution is the imaginary number, then there will be vibration. We'll see what's happening here. So A's general result will be looking like this. And by C square root, critical damping is 2 times of square root mk, like this. So decided by 2m is deleted, and this part becomes km. So what is left behind is minus h plus minus I times of square root of 1 minus h squared. So you can easily see that if h equals 0, then here is I, and h minus h, right? And if h equals 1, then this part becomes 0. And if this is larger than 1, it becomes I, and h will plus minus 1. So it becomes not an imaginary number. So put them back for x. So x is 2 case, positive and negative case, so with A and with B. So lab work is pretty similar. Look at what we did before. Let's look at A and B here, but we put out h omega t outside. So omega h, we define omega h with a look like this, because this part is the angular frequency. However, this angular frequency is with damping h. So once the damping ratio is decided, so the frequency also be changed. Because of the h, when h becomes larger, this part will be smaller. When damping ratio becomes 1 in the exact case, then this part will become 0. So that means there will be no vibration happens, because the frequency will become 0. So when it becomes 0, and this will becomes 1, so damping ratio will becomes non-damping case ratio. This also be true. But with gradually increasing of h, the damping ratio will decrease slowly and slowly. So with increased damping, the frequency will decrease. Thus, finally, we get this kind of equation. Change them to damping frequency, but here is elastic frequency. Keep it still. Let's look at about this part inside the bracket. It can be changed to this kind of expression during the Euler's formula that we did it before, and with a plus b and a minus bi sine wave here. So this is the same procedure we did before. Put the c out, and cosine cos and the sine phi, with a definition about like this. As a final resolution, we get x equals c, and with e minus h omega t multiple cosine omega h t minus phi. So see here will be the initial amplitude that's starting from 0 time. However, this will be the real amplitude with damping. We can see that the amplitude with damping will decrease with the time. look like the green one. And omega h will also depending on the damping ratio, so it's damped angular frequency. Damped angular frequency will decrease with the h, as we explained before. So that's the basic thing we want to talk today. Thank you for listening.